In this video, we will do the Stokes flow over a sphere, or creeping flow over a sphere. And in this configuration, we consider the following geometry. Z, then X, and then Y. And we consider a sphere sitting somewhere over here. Sphere of radius r, sitting right at the center. And the best coordinate system here is obviously a spherical coordinate system, and as such we do the following. We have a radius, so the radius of the sphere is r, radius r, and for spherical coordinates we have unit vector r, and then we also have theta. So this is the angle theta, so E theta is in this direction, but also this is a plane that changes, okay, and this changes, okay, and this angle over here is phi. This angle is phi. So E phi is in that direction. Okay. Now, for this flow, we're going to consider a free stream that is coming from the bottom at u infinity. So the streamlines will look like this. And same thing over here. It'll be nice and symmetric. Okay. So this is the configuration we're looking at. Now, if you remember, the Stokes equation was grad P equal to mu del squared u, and Stokes equations div u equal to 0. And then Stokes said, okay, how do we eliminate the pressure? We eliminate the pressure by taking the curl of the momentum equations. So this guy would give curl grad P is equal to mu curl del squared u. Now we know for a fact that the curl of a gradient is 0, and therefore this gives us the following identity: del squared omega is equal to 0, because omega is equal to curl u. So you take the curl that goes inside, that gives you del squared omega. Now this is in general for 3D. But then dealing directly with vorticity is complicated, because boundary conditions, BC's on omega, are not trivial. So for example, what do you do at a solid wall? What is the vorticity at a solid wall? And specifically in Cartesian coordinates, for example, the z velocity component is dv by dx minus du by dy. It's really annoying to figure out what we really don't know what the gradients are of the velocity at a solid boundary. So dealing with vorticity directly is really complicated. So one suggestion was, hey, let's deal with some type of symmetric flow and reduce first reduce the vorticity from 3 components into a single component. So this is 3 components to a single component. So consider 2D flows, 2D or symmetric flows, like in this flow over the sphere over here, where u r and u theta are not 0, but u phi is equal to 0. So there's this kind of rotational symmetry, and all the flow moves in the radial direction and in the theta direction, but there's no change in the phi direction around the sphere. And so what that does, it still reduces the equation. It becomes one equation, del squared omega is equal to 0. For this particular problem, omega would be equal to 0, 0 omega phi, because omega with the vorticity will be perpendicular to the other, to the two planes, to the other plane, which is ER, E theta. But still, we still need to make headway over here. This is still doesn't remove the problem of the boundary conditions for vorticity. So one idea is replace vorticity with stream function, because boundary conditions are the stream function are much easier to deal with. So for Cartesian coordinates, omega z is dv by dx minus du by dy, and u is equal minus deep c by dy, and v is equal to deep c by dx. So those two facts combined tell us that omega z is equal to del squared c. Now this identity is valid in or other orthogonal coordinates. Okay, you just have to change the meaning of the Laplacian. Okay, so then we're going to take this now and put it back in here, and this becomes del squared omega equals 0. This becomes del squared of del squared c is equal to 0, or nabla to the 4c is equal to 0. And this nabla to the 4 is called the biharmonic operator. Now, do we need a continuity equation? No, no need for continuity equation. No need for continuity equation, since C satisfies div u equals 0 by definition. Okay, so therefore this is the only equation that we are dealing with. And in spherical coordinates, the relation between the velocity, so in spherical coordinates, ur is minus 1 over r squared sine theta deep c by d theta, and u theta is equal 1 over r sine theta deep c by dr. So these two will help us figure out the boundary conditions. And finally, the Laplacian operator in spherical is equal to d2 by dr squared. You can find these in standard textbooks or on the internet. We'll give them to you in homework and exams. D by d theta of 1 over sine theta d by d theta. And you apply this twice, and then you will get the biharmonic operator, but we'll find that we don't have to do that because we're going to simplify this significantly as we go along. Now, what are the boundary conditions? Boundary conditions for the flow over the sphere. Well, at the surface of the sphere, we have no slip at the surface, so the kind of the velocity sticks, however that is going to look like. Okay, so u theta, in other words, u theta at r is equal to 0. But we also have no porosity, no penetration of the flow into the sphere. So ur is equal to 0 at r. Ur at r is also equal to 0. There's also one more boundary condition, and that's at infinity. At infinity, as r approaches infinity, we want the velocity, the total velocity, to be equal to u infinity, but in the z direction. Okay, so u infinity, that's what we want the velocity to be at r equal infinity. We want it to be aligned. Remember, this was our z-axis. Now, these two guys just tell us direct relation between, so they just tell us ur at r is equal -1 over r squared sine theta deep c by d theta at r equals 0, and u theta at r is equal 1 over r sine theta deep c by dr at r equals 0. But this last one is interesting because we need, this is, the boundary condition is expressed in terms of the z velocity component, so we need to translate that into something in terms of cylindrical coordinates. So if you take the origin over here, so x, y, z, at some distance in infinity, okay, infinity, we have that u, this is u infinity, great, okay, and this angle is theta, and the projection of u infinity on the r axis is ur, and the projection on the theta axis is minus, so this would be u theta. Okay, now remember e theta is going, so if this is er, e theta is going this way, and so at infinity we know that u at r approaching infinity, we know that ur is u infinity cosine theta, and u theta is minus u infinity sine theta. Now from these two guys, we're gonna try to derive a condition on psi, and that's doable. We're gonna start with u theta at infinity. So u theta at infinity, bad nomenclature, but it's the idea that at r, as r approaches infinity, u theta as r approaches infinity is equal to minus u theta, minus u infinity sine theta, but that's also equal to 1 over r sine theta deep c by dr. So this means that deep c by dr as r approaches infinity is equal to minus u infinity r sine squared theta. Now we can integrate this. Let's start a new page at infinity again. At r approaches infinity, we said that deep c by dr was equal to minus u infinity r sine theta. We integrate, that gives us psi still of r theta as r approaches infinity. That's equal to minus 1 over 2 u infinity r squared sine theta. We haven't set r equal infinity over here because obviously psi is not going to be equal to infinity. It's going to behave in this manner, but r is never strictly infinity, because then the velocity will give us the correct value. So psi needs to be a function of r. Okay, remember, it's the velocity that is equal to u infinity, not psi, okay? So we have minus 1 over 2 u infinity r squared sine theta plus some function of theta. Now we differentiate this d psi by d theta. That will give us, so we have a sine squared here, that will give us minus u infinity r squared sine theta cosine theta plus f prime of theta. Now remember the other boundary condition, u r as r approaches infinity is equal to u infinity cosine theta, and that's equal to 1 over r squared sine theta d psi by d theta. So that d psi by d theta from this condition is u infinity r squared sine theta cosine theta, right? So that's d psi by d theta, and so we have a negative sign over here, so we get the negative sign. Now what I will do is equate these two guys. So this guy cancels out with this guy, and this implies, when you equate them, that f prime of theta is equal to 0, and therefore f of theta is equal to a constant, and I'm going to set that to 0, okay? So set it equal to 0, otherwise we're just going to be carrying a constant all over. So therefore, psi r theta as r approaches infinity is equal to minus 1 over 2 u infinity r squared sine squared theta. This is actually a very useful condition at infinity, because it gives us the form, suggests a form for psi, which is f of r times sine squared theta. Rather than just f of theta and g of theta, you can set f of theta, g of theta, and then there's only one solution for g of theta, and that's sine squared. But it's the change happens in r as we approach infinity or get close to the surface of the sphere. So that's why this sort of solution makes sense. The next step is to take this general form and put it inside the biharmonic operator. Okay, so we'll start with del squared psi, and that's equal to d2 by dr squared plus sine theta over r squared d by d theta 1 over sine theta d by d theta, okay, of applied to psi, which is in turn f of r sine squared theta. So if we do this, if we process this through this operator, maybe it's a good idea to start on a new page. So del squared psi is d2 by dr squared plus sine theta over r squared d by d theta 1 over sine theta d by d theta of f of r sine squared theta. Now what happens? This gives us f double prime sine squared theta plus sine theta over r squared. Now f of r is gonna come out through all of this, so we get an f over here, and we get a d by d theta of 1 over sine theta. What if d by d theta of sine squared theta? That's 2 sine theta cosine theta, and then those guys cancel out, and then we get an f double prime sine squared theta plus f sine theta over r squared. What is d by d theta of 2 cosine theta? That's going to be minus 2 sine theta, and that gives us f double prime plus f over r squared, or minus 2f over r squared sine squared theta. So del squared c. Okay. Now if you call this little thing g of r, then the solution to del squared, then del squared c is g of r sine squared theta, and therefore by analogy del squared c will be g double prime minus 2g over r squared times sine squared theta. Plain and simple. Okay. Now let's go back to this guy. This guy suggests a solution for f of r of the form c times r to the power n. Okay, this generic form. Now, if you plug this back into here, we have a f double prime, so we need an f prime of r, and that's cn r to the n minus 1, and f double prime of r is going to be c into n times n minus 1 r to the n minus 2. Okay, so now if we put we put this guy back in here, okay, if we put this guy, we have cn n minus 1 r to the n minus 2 and minus 2 cr to the n minus 2, correct? Cr to the n over r squared. So if we put this guy over here, in other words, this is g of r equal, and that's equal to cn n minus 1 r to the n minus 2 minus 2 cr to the n minus 2. And then if we get cr to the n minus 2, we will have, if we factor out cr to the n minus 2, we get n into n minus 1 minus 2. And we factor this becomes n squared minus n, and then minus 2, and that's actually n plus 1 times n minus 2. So the roots for this guy, in other words, it's going to be n minus 1 into n minus 2. This is n plus 1 times n minus 2, so that gives you n squared minus 2n plus n, that's minus n, and then minus 2. Okay, so that suggests the general form for GR. Now when we take GR and apply it a second time over here, let's call this L of R or Q of R. Then if we apply the same idea, this f of r was CRN, was a solution to this guy, and then G of R, so that gave us a G of R solution that looked like this. So the solution for Q of R would be by analogy similar to this guy, except for the fact that instead of n, we want to put n minus 2. So we will still have the n plus 1, n minus 2, and then we would have same multiplied by 2 more factors where n is replaced by n minus 2. So this would give you a general solution of Q of R is equal to C R to the n minus 2, okay, C R to the n minus 2 times n plus 1 and n minus 2. And then if we put n minus 2 over here, we would get n minus 2 plus 1, we get n minus 1, and n minus 2 minus 2, n minus 4, n minus 4 in terms of total factors, okay, or the factors that matter. Now it is, remember, we're still after n, okay, we're still after the value of n. How many n's do we need for this f of r? And those you can obtain from the roots of this guy that make this whole thing is equal to 0. And then you get n equal minus 1, and then n equal 2, and then n equal 1, and then n equal to 4 over here. This guy. Okay, so that would be the general form, the however many n's we're going to have for CRN. So finally, the solution would be f of r is equal to, we said that the factors that matter are n equal 1, 2, 4, and minus 1. And the way we're going to write this is we start C1 r to the minus 1 plus C2 r plus C3 r squared plus C4 r to the 4. Okay, so that gives us the general form for f of r, and still our solution is psi r theta is f of r sine squared theta. Okay, so now we apply boundary conditions. Apply BCs. Starting at infinity, as r approaches infinity, we said that psi was equal to minus 1 over 2 u infinity. If you remember, that boundary condition was a couple of pages ago. At infinity, psi was minus 1 over 2 u infinity r squared sine squared theta. Okay, and that's equal to f of r, which is c1 r minus 1 plus c2 r plus c3 r squared plus c4 r to the 4 sine squared theta. So the sines cancel out, sine terms cancel out, then we divide by r squared. What we get is c1 over r cubed, right? So 1 over r divided by r squared plus c2 over r plus c3 plus c4 r squared, okay, is equal to minus 1 over 2 u infinity. Now this guy goes to 0 as r approaches infinity. Naturally, this guy goes to 0 as r approaches infinity. We can't say anything about C1 and C2. C3 is not affected by r. However, this guy necessarily goes, C4 must be equal to 0, otherwise this term will go up. And therefore, this implies that C3 is minus 1 over 2 u infinity. And we obtained our first constant, okay? And then our other constant, C4, is equal to 0. So this simplifies f of r. Now, no slip, the other boundary conditions, and no slip boundary condition was that u theta equal to, remember what was u theta? Was equal 1 over r sine theta deep c by dr, all at r is equal to 0. So this implies that 1 over r sine theta, or really it's just deep c by dr, is equal to 0. Deep c by dr at r is equal to 0. This implies that f prime at r is equal to 0. Now what is f prime? F prime is equal to minus c1 r to the minus 2 plus c2 plus 2 c3, and at r that's equal to 0, so that implies minus c1 r to the minus 2 plus c2 plus 2 c3, so this is 2 c3r is equal to 0. And then the other boundary condition, the no penetration, we had ur is equal minus 1 over r squared sine theta deep c by d theta at r was equal to 0. This really implies that f at r is equal to 0, or in other words, c1 r to the minus 1 plus c2 r plus c3 r squared is equal to 0. Remember, we do have c3, so we're not worried about that. Okay, so that's one of the equations for the boundary conditions. We're still missing C1 and C2. Let's call this guy equation 1 and this guy equation 2. So we know what C3 is, so we just need to eliminate the other constants. So let's start by going after C1. So to get C1, let's see, what are we going to do? We need to eliminate C2 because we know C3. So if we multiply equation 1 by R and subtract it from 2, so if we do 2 minus R times 1, that's equal to 0, right? So and equation 2 is equation 2 is CR to the negative 1 plus C2R plus C3R squared plus C2R plus C3R squared minus R times 1. So that gives us minus C1R. So we have a minus C1R to the negative 1 minus C2R, right? And minus 2C3R squared. Minus 2C3R squared, that's equal to 0. So these guys cancel out. C1 over R plus C1 over R, so that's 2C1 over R minus C3, so we have a 2C3R squared plus C3R squared, we get a minus C3R squared is equal to 0. And remember that C3 was equal to minus 1 over 2 u infinity. It's 1 over 2 u infinity. Okay, don't forget that. So this tells us that 2C1 over R is equal to C3R squared, or therefore C1 is equal to C3R cubed over 2, and that's equal to minus 1 over 4 u infinity R cubed. And that is C1. And then you substitute for C1. I'm not going to carry out the algebra. It's just really straightforward. This gives you also C2 to be equal to 3 over 4 u infinity times R. And now we have the full set of constants for f of R, and therefore C, which is equal to C1 over R, so that's minus 1 over 4 u infinity R cubed over R. Remember F, the definition of F was C1 over R plus C2 3 over 4 u infinity R, right? Plus C3R squared, which is minus 1 over 2 u infinity, C3 is minus 1 over 2 u infinity R squared. And this also gives you the remaining velocity components. UR is u infinity, tightly organized here, minus 3 over 2 R over R. R is the radius of the sphere, plus 1 over 2 R cubed over R cubed cosine theta. And this whole thing is multiplied by sine squared theta, obviously. And then u theta is minus u infinity into 1 minus 3 over 4 R over R minus 1 over 4 R cubed over R cubed sine theta. Finally, the pressure can also be obtained from this distribution by substituting into the Navier-Stokes equations, and doing that substitution you get dP by dr, and this is where you get viscosity. And the interesting thing is that in our solution for the velocity there's no viscosity in the expressions for the velocity, there's no viscosity, but that shows up in the expressions for the pressure. So dP by dr is 3 mu u infinity over r squared, radius of the sphere, times r over r cubed cosine theta, and dP by d theta is equal to 3 over 2 mu u infinity over r times r over r squared sine theta. You can find from these the pressure distribution to be P is equal to P0, and if you want to include gravity as well, you can do that. Minus, so we have P0 minus 3 over 2 mu minus mu times u infinity over r times r over r squared cosine theta minus rho g z. So that gives you the pressure distribution in the entire flow. From that you can obtain the drag on the sphere, etc. And that completes the solution of the Stokes flow or the creeping flow over a sphere.